All right, good afternoon.
Good afternoon.
Yeah, I
Afternoon.
think I got my computer weirdness worked out.
Can I start off by saying that was a very fun but kind of a crazy assignment?
Awesome.
Yeah, I like pointers are, like you said before, they're kind of weird if you don't know the behavior of them. So to have this assignment, it really kind of clarified all that.
Okay, good. Well, that's exactly the goal. Um, it's it's a potentially really painful assignment, but on the other side of it, you're in really good shape to do lots of things with pointers and therefore lots of things with data structures. So hopefully it's worth.
It's funny. The add function took me about a day and a half to figure out, and then search, delete, and print took about 5 minutes.
Right? Yeah, that can definitely happen.
I finished it about a week ago, but I look back on it and I feel like I would have had a much smoother time if I broke the add function into at least 3 functions
Okay.
to like ease out the logic.
Mm-hmm. Okay, yeah, I could see that.
Funny is I did the same thing where I had just the add function and I was implementing another function into that one of the functions we're supposed to write. I don't want to give too much information on it, but I ended up testing my code. I was getting ready to turn in, and I had a segfault thing.
Oh.
I didn't cover a case in one of the other functions, so I went back and rechecked all the logic and was able to find the issue with GDB, which was kind of cool.
Awesome. Very good. So yeah, this is all good experience. Let me just mention though that definitely for a lot of students, at least traditionally in this class, pointers don't click this quickly. It can take getting maybe halfway through the course before it really starts to feel like, wait a minute, I think I understand what's going on here. So PA1 is a step in that direction, and if it's helped you get to a point of clarity, that's fantastic. And if you don't feel like you're at the point of clarity yet, don't worry about that, right? Just keep working on it. And the more you try to understand your code, and particularly the more bugs you run into, and the more you face those bugs and resolve them one at a time, the more things will clarify, and you will get there, right? It's not an if, it's a when. And it just takes your brain sort of like figuring out how to map these concepts, and once that's there, then you're totally solid for algorithms, data structures, stuff like that. So we're in an unusual situation this quarter because because we're splitting classes between remote and online. We're doing them on alternating days because I didn't want to teach in person and then have to run home to do the remote teaching. So those are on alternating days. So we have these 2-hour classes. So we have 2 meetings per week. And we have 2 Monday holidays, which means, this coming Monday, Martin Luther King Day, the other section of 222 does not meet. And so we basically lose half a week of lecture in that section. We gain a half a week of lecture in this section. And that's going to happen twice. I think it happens on President's Day in February. So we get like an extra, basically an entire week of lecture material in this section compared to the other one. And so I'll try to keep the sections somewhat in sync, but it means we have definitely a lot of breathing room in this meeting. If there's questions, things we want to go over in more detail, and so on. If we end up, ahead of the other section at the end of the course, that's great. We'll go into some other bonus material. We're not going to run out of things to talk about or work on. But definitely, particularly in this section, you're encouraged to ask questions, ask for clarification, things like that, because we definitely have some breathing room. So any other?
have a question.
Yeah, go for it.
In the assignment, it was saying that all the functions have to be into one.c file. I'm used to having just one function in a .c to reference to. How do you do multiple in one of them?
You basically just list them all one after another in a file. So let's try that.
Like I'm used to doing the boolean thing while doing functions at the bottom of a main, but I wasn't used to doing a call to one. Because
Okay.
when you call like the entire file.
So yeah, let's look at how we can set this up.
Just yeah. Please and thank you.
All right, so I've got a function. I'm just going to call it fun. That takes an integer and returns an integer. I've got a new function that takes an integer and returns an integer. So let's make a functions.c. And let's just say it returns twice the integer. Is it new function or function new? New function. So these are bogus functions, right? But it's just so we can compile some stuff. So in your functions file, you just list your functions one after another, and when you link everything together on one big GCC line, the linker will know that inside main you're calling fun. It will look for some file that you compiled that includes a function fun, in which case it would pick up this one, and same with new function.
Quick question.
Yeah.
I added the header to the top of that.
Mm-hmm.
Just because I had an issue where it wouldn't compile
Mm-hmm.
the header. So I just added, that doesn't really affect anything, right? It shouldn't.
It shouldn't affect anything, but let's go ahead and put in a main.h in here. So when you try to compile, you're getting these warnings. Let's break this down. Implicit declaration of function fun, and it says integer I equals fun parentheses 5. So implicit declaration means that I have not actually declared what the function fun is, right? So when I say something like integer I, I'm declaring a variable. I'm saying I is a variable of type integer. When you declare a function, you're saying this is a function named such and such. These are the arguments it takes. This is the type of thing it returns. When I compile, it's saying I have not explicitly declared what this function is. So it's making an assumption. It's doing an implicit declaration. And it's deciding what this function is based on how I'm using it. I'm returning something that I'm saving into an integer variable. I'm passing something. Well, 5 could be an int. It could be a double that I just didn't put a decimal point after. It could be a character. So it's probably assuming this is an integer. And so it's pretending that I said, integer fun parentheses int. But it's warning me that it did that. Because if I actually wanted function to take a double number as an argument, it would be making the wrong assumption. So the way we avoid all of that is to prototype our functions. So in the beginning of our file, before we actually use the function, we do something like this. And that's telling the compiler, hey, when you get around to seeing me call a function, it should get an int, it should return an int. So this 5 will get used to generate an integer value 5 that'll be passed as the argument to this function. And the return value, it'll assume the return value is an int, which means it will just copy it byte for byte into this variable I. And that should get rid of all of those warnings. But if I have other files that use these functions, fun and new function and so on, I have to type in that declaration everywhere that I use these functions. So we can do something different. We can make a main.h and put those function declarations in there. And then instead of doing this, we can say include, and we do double quotes to say in the current directory, main.h. And that'll include our function prototypes, and then when we compile, again, we've got no warnings. Now in my functions.c, if I wanted to do something like, if my fun function was going to use the new function, right, take the argument and run it through my new function and then return twice that, right, I'm going to get these warnings again. Oh, I also forgot a semicolon. But I'm going to get these warnings again because inside functions.c, I'm also doing an implicit declaration. I'm calling new function and I haven't told the compiler what new function is, what it takes, what it returns. The first time it encounters new function is when I'm using it, and so it infers from that what this function should look like, what it should take, what it should return. So I should prototype my function in here too. Well, since I already put my prototypes into an include file, I can just say include main.h, and now my warnings are gone.
Okay, this answered my header question.
Mm-hmm.
Okay.
Awesome.
Thank you.
Yeah.
I had a bit of an argument about this with somebody the other day.
Yeah?
That you generally don't want to touch your header files because it does pull replace on every one of your C files. So if you can have all your prototype declarations in your header and just define it in different C files, you need to compile less. And that person was arguing that headers and C files shouldn't make any difference on compile time, but do they in this case?
There's two ways in which we can interpret your question. So in terms of make files, right, if you touch a header, it will force make to generally remake anything that depends on that header. But if you're actually talking about the compile time, when the compiler does this include, it's going to basically open up this file, read its contents, and take all of the lines it finds in there and pretend that they're right here in this file. And it's going to compile, more than just this. It's going to compile these lines of code, but it's also going to have to go through all the lines of code that it finds in here. And if I had, a lot of stuff in here that I didn't need, then potentially, it's needlessly taking longer to compile my function, my file. But it's usually not a big issue. It's usually, a pretty small difference. I mean, it's unusual to have a header file that's going to be very demanding on the compiler, because it's mostly a bunch of defines and macros and prototypes, structures, things like that. So there's a CP preprocessor, which is run before the actual compilation runs. And so if I run cpp on main1.c, you can see what's being fed to GCC, right? There's my code that I actually typed in, but there's also all this other stuff that's coming because I included main.h, right? So when I said main.h, it included these other lines. And yeah, those have to be compiled.
I guess what I was trying to get at was, if you were to say you have some useful function that you want multiple scripts to be using, and you may change that function quite a lot over the course of your development. It would be ideal to put it inside of a source file instead of in the header and keep changing it in the header, because all those scripts that are using that header file have to be recompiled, right? Because it's basically coming in and replacing, putting all that is in that file in the source files, right?
That's definitely true.
Okay.
But more importantly, don't put executable code inside .h files. It's really not what belongs in there. If you're writing a function, right, a bunch of C statements that represent a function that's going to be called, those really should go in a .c file. And then when you change the function, you would only recompile that .c file. You would have to relink the main program to you know, make the executable use that new compiled version of your new function code. But we really don't want to write a function inside a .h file. And in fact, if you try to do that, like let me do this.
So real quick, just so I have clarification, are you saying, so like, in this case, the prototypes are always going to be the same that you've declared it, unless you, for some reason, change the value coming back. So even if you change up the function, it shouldn't recompile the .h, right? It'll only recompile the functions.c or whatever that function is in, right?
Right, right.
So as long as you're not changing the prototype, it will still not change the .h.
If you're not changing the prototype, you should not have to change the .h.
Okay.
And then, you know, random code.c that includes this .h file would not get recompiled by your makefile typically.
So this would, his only problem would be if he decided to change the prototype of the function altogether, like instead of an int, he now needs a double to come back.
Right, if you change the prototype, then you need to change the .h file, and now everything that includes that is going to have to get recompiled.
Okay.
So here's something that's, you know, bad to do. I'm putting a function inside my .h file, right? And if I try to do that, I'm going to get load errors. And it's telling me multiple definition of bad. Why is it doing that? Because main1.c is including main.h. Functions.c is including main.h. So it's as if I had typed this function declaration inside two of my .c files. And that's not something we would normally do, right? When you make your init function, you're going to put it in one file, functions.c. You wouldn't write the same function with the same name in 5 different .c files. Because, you know, that doesn't make any sense. But if I put a function in my .h file and I include this in multiple files, that's exactly what I'm doing. I'm making multiple versions of my function. So don't do this, right? You can put in prototypes and say, hey, you know, somewhere I'm going to define this function bad. And even if I don't define it, that's okay, because nothing is ever calling it. But if something had made a call to it, it would have known what this looks like because I've prototyped it. I said this is a function, takes no arguments, returns an int. And just for completeness, to finish up talking about the preprocessor, right? If you include standard IO.h, which you include, you know, whenever you're going to be doing IO, and I just do the preprocessor phase of the compilation, I get a lot of output, right? All of this is being fed to GCC, and there's several hundred lines of additional C code that has to be compiled. But it's mostly, you know, just declarations. Here's an array called _unused2. It's an array of characters. Here's a structure called IO file plus, right? These are things that the compiler just kind of like goes through, and it doesn't really get bogged down on it.
I didn't know you could interact with the preprocessor this way. This is cool.
Yeah, this is Unix, so you can do all this stuff, and CPP, you can give it a bunch of switches. I don't know what most of them are, but it's called automatically in the beginning of compilation. I think GCC probably has switches you can use to manipulate how CPP runs and should it save like a copy of the output and so on. Just like GCC, you can do a -s to say, hey, after you convert the C code into assembly language, leave that assembly language file around. And so we've got a main1.s, and we can look at that and see the assembly language that the C code was compiled to. And since this is an x86 machine, these are Intel x86 instructions. If you do this on a Raspberry Pi, you would see ARM instructions. If you do this on a PIC processor, you would see PIC instructions. But normally, this conversion to assembly language happens, the code gets compiled, and it's all kind of happening in the background. But if you want, you can look at this code, and you could actually take this assembly language code and compile it with GCC, and you can make changes to it, and so you can do assembly language development still using the GCC command, because it's all open and documented, and it's there to work with. So this is part of why Unix is so popular in the classroom, because it really exposes all of these details. And if you're studying computer science, right, you want to learn all of these details. You don't want a mysterious closed box that you click on something and something happens and you have no idea why. So this definitely is an environment that supports digging into it and taking the cover off and seeing what's going on.
I think I saw that command in my GCC binaries folder, and I was confused because I thought it was the C++ compiler. C++,
Oh, right. Actually, yeah. That's interesting. Yeah, because now that you say that, I would have thought that was.
C++ too.
Yeah.
I don't really looked into this all a lot.
I think it also does Objective-C also.
Ah, interesting.
I'm not sure.
So G++ actually links to the GCC man page, and GCC actually says it's a C++ compiler. So it's all one big happy family.
By Objective-C, are we talking about C#?
No, it's a different language.
Oh, gotcha.
I think it's Swift now, but I'm not sure.
Oh, isn't Swift Apple?
I thought that's what Objective-C turned into, but I
Okay.
I might just be making that up.
Sounds familiar. And it's all moving targets too. Say again?
A lot of the game engines now will interpret things into like Android, Apple, all that. If you're doing mobile game development.
Right. I've seen some of that.
Pretty cool.
Yeah.
And Objective-C did turn into Swift. It's for iOS and Mac. And
Okay.
it's kind of like Java-esque instead of like C. Where
Cool.
.NET is for all the desktop and Microsoft applications.
Mm-hmm. The ecosystems are there's a lot of different environments out there, and there's no way that you can sort of keep up with all of them. But after you've worked with enough different environments, after you've done C down to a very low level, you've done assembly language, you've done machine language, you've gone to the other end of things and done something high level object oriented like Java, and you've worked with a few platforms like Unity or Unreal, or you've done Android development or things like that. After you've done enough of these things, you start to get really good at learning new systems. And so if somebody comes at you with a new language or a new development environment that you're supposed to be working in, the time it takes to get up to speed in that gets less and less the more you do it, until eventually it's like, okay, give me a day, I'll go read up on this, and then I can start working on this tomorrow. And that's a fun place to be, because then when something new comes along and it's super exciting and you want to jump into it, you can do it. You don't have to take a class in it or something like that. You can just sort of recognize how it relates to what you already know, what the differences are, figure those out, and then you're up and running. So so main.h, let's just review what should be in your main.h. Definitely, you know, prototypes. Well, first thing that should be in there is probably your definition of your structure. So what's a my node? It's an integer. I think I called it data. And a struct my node called next node. So that's got to go in there because every function is going to, every file is going to need to use a my node at least once. Your main program needs it for the Sentinel node mylist, and the functions.c needs it all over the place. And then put in your function prototypes, because you're going to declare the search function inside functions.c, but you're going to call search from main. So main needs to know what the prototype for search is, and you may call main from the add search from the add function, because when you're trying to add a number, you know, you may want to know if it's already in the list, or delete, for example. You may want to know if it's in the list before you delete. Add, you don't care. So put your prototypes in here, right? Integer add struct my node pointer comma integer. And you know, I usually like putting comments in here, just you know, because it's another place I can go and have all of my documentation of my functions in one spot, and that's handy. I'm definitely going to put comments, you know, around each of my functions when I'm actually writing them, but it saves me from having to write a separate block of comments, you know, somewhere else that say, oh yeah, the add function does this, this does that, and so on. So this is a handy place sometimes to put another, like a one-liner that just kind of reminds me what my functions are. And those are probably the only things you need to have in a main.h. You might do like pound defines, define sentinel value 1, 2, 3, 4, 5, 6, 7. So a pound define basically says, hey, anytime you see this, replace it with that. And so inside your init function, you're going to say, you know, once you've allocated a sentinel node, you're going to say, hey, set this thing's data value to 1, 2, 3, 4, 5, 6, 7. Well, instead, you could set it equal to this thing called sent value, and in your main.h, you could declare what that is. And the advantage of that is, you know, if you're using this code somewhere and they say, well, we want the sentinel to have a data value of -1, you don't have to go into your C code and change a C statement. You can change a header file. And changing header files somehow feels a little less scary than actually rewriting C code. And so particularly if you were using somebody else's package and it set the sentinel to this value and you were supposed to set the sentinel to a different value, right? It's pretty painless to come in here and just change this one piece of this .h file to whatever the new value is. And you know, maybe there'd be a comment here which says, you know, flag save in Sentinel's data field. And now it's like, okay, I'll just change that number from one thing to another thing, instead of actually going into the C code.
Function macros. Like, I notice sometimes things that use C and C++ as their programming language, whether it be game engines or APIs or what have you, they'll do a lot of macros.
Yeah.
Just to keep your code base simpler. But I think it's also a speed measure too, right?
Partially. So a macro is part of the preprocessor. So, for example, we can define symbols that say, you know, if you see this symbol, replace it with this. We can also define symbols that take arguments. And so, for example, I could say, you know, define my absolute of n to be the following. N bigger than 0, question mark, n colon minus n. And in my code, you know, I could say something like, you know, I equals my absolute x. And it looks like a function call, but in fact it's a macro expansion. And the preprocessor would say, okay, my abs is a macro, n is x, and so it's going to replace this my abs parentheses x with paren x bigger than 0, question mark, x colon minus x. And this is a way to write an absolute value, right? This is a way to say, hey, if x is bigger than 0, I want to use x. Otherwise, I want to use minus x. And that's, you know, certainly going to be faster than calling a function, because function calls are expensive. You have to save where you are, right, on the stack. You have to create a new call frame with new space for local variables and so on and so forth. You have to jump down to that new location, which may mean flushing your cache memory and so on and so forth. You execute this you know, code that corresponds to this, and then you have to do a return, which brings you back and changes the call frame and flushes cache and all that kind of stuff. If you can do this in line, that's going to be faster. And so that's one reason some people do this. For us, we're not really worried about speed. We've got, you know, CPUs that will do quite literally billions of things a second. And so we you know, are usually pretty fine just making a function call. Not a big deal. But yeah, that's one thing you can do with macros.
I was informed at one point on an online course I was taking, he just cautioned against using inline functions because sometimes it would, he would caution against it when you're using complex logic. Do you know anything about that?
Well, I can tell you a personal story why this can get you into trouble.
Go for it.
So here's a myabs function. It replaces, you know, myabs n with this. So if I say I equals myabs x, right, it replaces it with x bigger than 0, question mark, x colon x minus 1. Well, that's fine, but suppose I want to do something like this. I equals myabs x plus plus. So I want to take x, take its absolute value, save that in I, and then I want to increment x. And guess what this expands to? This expands to x plus plus bigger than 0, question mark, x plus plus, colon, minus x plus plus. And if I have x equal to 5, I'm hoping I is going to be equal to 5, x is going to be equal to 6. No, x is going to be 5, it's going to look at x, compare it to 0, increment it to 6. Since it's bigger than 0, it's going to take x and return that, but it's going to increment x again to 7. This is going to increment x twice. And that's a fairly classic problem. That's what I call the hardest bug in the world I ever found. It took me about 2 or 3 weeks to find that. And it was about 4 hours a day of debugging. So, you know, it was a good chunk of time.
Learn through pain.
Yeah. And that was a major aha moment of, like, you know, how this can catch you in macros. But I found it by, you know, in GDB, something equivalent to GDB, just going through one line at a time. What's supposed to happen, what happened, what's supposed to happen, what happened. I just did that until something didn't make sense. And that's what it turned out to be. So that might be one reason people say, you know, avoid complex logic, because things like this can sneak up on you. I'm not familiar with Rust. Yeah, go ahead.
The delete function for the programming assignment, I remember, I think it was the second lecture, you said that we're not going to have any duplicates for delete that we have to worry about?
Mm-hmm.
Okay.
Yeah,
So
but they shouldn't
the
affect you
random
anyway.
instances.
Delete shouldn't be affected by duplicates anyway. Assuming that, you know, if something appears in the list more than once, delete just deletes one of those. That should be fine. That should be what probably happens automatically, but I won't test it with that.
Oh, I thought it said in the actual description that you should not add a second one of the same node.
Right, which is why I'm not going to check it.
Oh, okay.
The add function
Well, no,
should be
for
able to
me-
do that, though.
Yeah, because well, it shows in there. It says node already found. So success, cannot add out of memory or whatever, and then node already found.
Right,
is
right.
the third option for add.
Mm-hmm.
So I just made it so it can't add a duplicate.
Well, the add function should be able to add, though.
Oh, okay.
But the main program will stop you from being able to do that.
Oh, okay.
Because what's your add function going to do if you call it and you try to add something that's already in the list?
Oh, it just returns as another or a different status. I think is what it returned a status that said it was already in the list, and so the main function just kept going.
Like a 2 or something like that?
Yeah.
Okay, so yeah, that's different from the required behavior of the add function. So make sure you do it exactly like what's described.
Okay. We can resubmit, right?
Yeah, you can resubmit until Friday at 8. Once it's submitted after Friday at 8, I'll grade it as is.
Oh, gotcha. Okay.
Yeah. Let's see. My takeaway from this discussion is just to avoid macro functions unless you really need optimize for performance. Maybe, maybe not. Sometimes macros are really useful. Sometimes they let you do things that are harder to do with actual function calls. I mean, if you really, really want to just sort of write some code without having to write it out by hand every time, macros can definitely be useful. They're also really useful in things like Engineering 270 when you're doing assembly language because, you know, assembly language is such a quirky language, and maybe there's things you do over and over and over again, and you don't want to, you know, make a function call, but you want to just sort of generate some code on the fly. That's where macros can be handy. Or maybe you're tired of writing printf every time that you want to print an integer value. Well, you could make a function that you call, but you could also just make a macro. Takes a number and just says, you know, printf %d \n, and go from there. I don't know where you're supposed to learn about macros, though, because I don't think they go very deeply into them in 121, and I don't really talk about them in 224, and I'm only talking about them today because we got time. But I don't know where people are supposed to learn about those. And I think I kind of picked them up sort of on demand, like I needed to do something and dug into it. Someone said a lot of built-ins are just macros. This is definitely true, not just for Rust, actually, in C. A lot of function calls that we make actually aren't function calls. They're really just wrappers. All right, good. Other questions, comments, PA1 or whatever?
Alright, sorry, just to verify, the add function, if it's already on the list, returns the 0.
No. The
Okay,
add
so
function says nothing about duplicates. Right? The list should remain sorted smallest to largest. If you insert a number, return 1. If you're out of memory, return 0. So add does nothing special with duplicates, but your main program, when you say I a number, that should print out either success if it inserts, node already in list if the number was already in the list, and out of memory if it's out of memory. So in your, go ahead.
Call it.
Yeah, so in your main program, if someone says insert n, first thing you want to do is search for n. If it's already in the list, print out node already in list. Otherwise, go ahead and call your add function. If it returns 1, print success. If it returns 0, print out of memory.
Okay, yeah, sorry.
Okay, no problem. Yeah, I could have made that more explicit. I wrote this up the night before I posted it, so I will make that more explicit next time. Let's see, if we need to use a skip day for PA1, we don't need to let you know. Instead, just turn it in by 24 hours past the due date. Yep, that's exactly right. So, so just don't submit it until you're ready to submit it. As soon as you submit it after the due date, I'm going to take that as your submission. So if you turn it in, if it's been submitted by 8 a.m. Friday morning, I'm going to grade that, and it's not going to cost you any skip days, but I'm not going to let you turn it in after that. So if you want to turn it in late, just don't turn it in until you're ready. Oh no, you functions in Unreal. Oh.
They're huge. If you go and look at the definitions, they're just massive.
Unreal is such a beast, man.
Right?
Yeah, I've tried to dabble with it and the blueprints and stuff like that, and I feel like if I had, a lot of time to really just kind of like dig into it from the ground up and explore, the low level stuff, the high level stuff, it would be super fun to play with. But it doesn't feel like it's for the faint of heart. It's and all the documentation I ever found on it was like written by people who are experts and are assuming you're an expert. And the beginner tutorials that I found were like, follow these 500 steps and you'll see a ball bouncing on your screen. And that's great, but I have no idea what those 500 steps are. It's just, monkey see, monkey do. So it's always been a challenge for me.
So I'm in a Java class right now, and we're talking about classes and how those extend each other in superclass, thing like that.
Cool.
I find that very helpful when it comes to C++ or C#, or Unity. I can't remember what they're in, but basically, I'm doing a Udemy course also to help me kind of learn Unity and all those. And I find that with the information from the classes and learning how to extend them and what they actually mean, it helps a lot interpreting what the logic is.
Okay, cool. That's good advice.
One last little note there.
Mm-hmm.
I found a really, really good step-by-step Unreal course on Udemy.
Oh, really?
And I basically sat down and spent my whole summer break learning it. I spent like 3 weeks doing it.
Wow.
I got about 3 projects done, and the last one was like a tank game.
Oh, cool.
And it was really insane.
Awesome. That's cool. Can you post the name of that or a link to that course, like in the discussion or something?
Absolutely.
Or pop it on Discord, because that would be good to keep for future reference. Cool, thanks. All right. Well, let's talk about our next data structures, and we're going to use linked lists in some of the implementations of these structures, but we'll also look at other ways to do these. So these will be a little lighter weight than what we've been doing so far. This is going to be more emphasis on what these structures look like, and less detail on like how we implement them, maybe. And I don't know if we're going to do a programming assignment on these or not. I've got to decide what PA2 is going to be. But these are really important structures anyway, and they'll come up throughout the course. They'll come up in 223. They'll come up in CSE215 and definitely in other classes. So I want to talk about stacks and queues. And I want to start with stacks because they implement a little easier than queues in some ways. And they're a little more familiar to us, even if we don't know, don't realize that they're familiar. All right, I'm gonna screenshot that. Thank you. All right. So what is a stack? And when we talk about data structures in this course or 223, we're gonna break our discussions to kind of two pieces that'll intermingle. One aspect of a data structure is simply what does it look like to a user? How do I interact with this? So this is, like the main program in PA1. What does it know about a linked list? Well, I can initialize it, I can add, I can delete, I can search, I can print, and I can clean up. And the main program doesn't know about sentinel nodes, and it doesn't know about nulls and pointers and all that kind of stuff. It just knows about these 6 functions. And then there's the implementation of the linked list, which is your functions.c, and that doesn't know anything about the main program. It doesn't know about the p command and the prompt that looks like a greater than sign and all of that. It knows about the linked list. So as we talk about data structures, we're going to sort of think of these two views of it, right? What does the structure look like to the user who's using it? And then how is this structure implemented? What does the code look like that makes this data structure actually happen? So let's look at the user perspective of a stack. A stack is a place where we can store things and retrieve things. Okay, that's what we do, a lot of in computers. We store things and we retrieve them. And so what can I store on my stack? Well, let's suppose I store a pen, and then I store a remote control, and then I store a pair of cufflinks. All right, so those are stored in my stack. The peculiar thing about a stack is I generally don't go back and pull something out of my stack except for the last thing I put in the stack. So I can't say give me the pen, I can't say give me the remote control, I can't even say give me the cufflinks. All I can say is give me the last thing that I gave you. The last thing I put in the stack was the cufflinks, so I can say, okay, give me back the last thing, it'll give me the cufflinks. And those are taken out of the stack. And now if I say give me the last thing I gave you, what was the last thing that I put in the stack before the cufflinks? It was the remote control. It'll give me the remote control. Remove that from the stack. And now I can say, okay, I'm going to add a mouse to the stack. So now the stack has a pen and a mouse. And now I'm going to add a glass of water. And now I can say, okay, give me something back from the stack. It'll give me the glass of water. And I can say, put a remote control on the stack. So there's a remote control. And this poor pen that I put in there in the beginning of this, that's just sitting in the stack waiting to be removed at some point. We're never going to remove it until we removed everything else that was put in after that. So I can remove the top, which is the remote control. I can say, give me the last thing, that's the mouse. And now I might say, give me the latest thing that was put on the stack, that would be the pen. All right, that's the basic interaction with a stack. You put things on the stack, you remove them from the stack, but you remove them in an order which says the thing I want to remove right now is the last thing that I put in. And so, yeah, as someone just said in chat, this is called a LIFO, which is short for last in, first out. The last thing you put on the stack is the first thing that comes out of the stack. And so another way to think about this, let me see. Instant props here. So I'll steal my daughter's Pokemon cards. So imagine that my stack is sitting here on this tabletop, right? And I put a else on my stack. And now I put a boss's order on my stack. And now I put Cheryl on my stack. And now I put Turbo Patch on my stack. If I say, give me the last thing on the stack, it's going to give me the last thing that I just put in. The last thing I put on is the first thing that comes out. And if you think of your stack as, just a neatly piled stack of objects, the only thing I have access to is that last thing that I put on, which was Turbo Patch. And if I remove that, then I have Cheryl sitting on the top of this pile, the top of this stack, and I can remove that if I want, or I can put something else on the stack. So I put on a cape of toughness, and now that's what's sitting on the top of this stack. And if I remove cape of toughness and I remove Cheryl and I remove boss's order, right? What's left on the stack? The very first thing that I put on there. So this is also like a first in, last out, right? But the acronym is always LIFO, last in, first out. But the first thing I put on there is going to be the last thing to be removed. And if I decide, you know, to pop an energy card on there, well, that's sitting on top of that first card. If I remove that and then I say remove, you know, what's at the top of the stack, I get that card back, but now the stack is empty. There's nothing there. Yeah, I looked at Target for Pokemon cards before Christmas, and the whole section was bare, which I was kind of surprised. I used to buy Magic cards at Target all the time, and they had Magic sets, but no Pokemon. So.
Good old scalpers.
Yeah, but I finally learned how to play Pokemon, so
Actually, they took those out of stores because people were having meltdowns when they were trying to buy multiple packs, and the store had a restriction on how many packs you could buy.
Really? So is this like
Online only.
Is this like a recent thing, like a Pokemon shortage?
Yeah. Well, like I mean, yeah, over the past year or so, but about 5 months ago, I want to say, they took them out of stores.
Wow. Interesting. Okay. All right. So that's. Yeah. Go ahead.
I have a question about stacks, and if we're gonna get to it.
Yeah.
I'm still kind of unsure what happens when you call a function and gets put on the stack, as in is it allocating memory just for the variables or for the entire function to be called? That's something I still find kind of confusing about the stacks.
Well, let's let me do a little bit more definition about stacks, and then we'll talk about applications, and that'll be a great application to talk about, which is how it relates to function calls. But let me do a little bit more conceptual development first. So the main ways we interact with a stack are through a pair of functions. Push, which takes the thing we want to add to the stack and adds it to the stack. And so if we had a stack of integers, I could say push, and I could give it an integer argument, and it would add that to the top of the stack. And when I want to read something out of the stack, I call a function pop. And it doesn't take an argument because it's just saying, you know, give me what's on the top of the stack. But it might return, you know, an integer in this case, or a Pokemon card or whatever. And so those are my main pair of functions for adding to and removing from a stack. And there's two exceptions that can happen. If I've removed the last thing from my stack and my stack is empty, so if my stack is empty and I say pop, that's an error condition. That's an exception. Because there's nothing on the stack, but I'm saying, hey, give me something more from the stack. Well, there is nothing more there. The stack's completely empty. I can't pop anything off the stack for you. And so this is a condition called a stack underflow. The other possibility is that your stack can be full. Because, you know, the stack takes memory. We've got to have a place to store the things that are in the stack. And sometimes, you know, we can use all the memory available in the machine. Sometimes we define a stack to only hold a certain amount of stuff. So imagine you're going to, you know, stack books on your desk. Well, there's a limit to how many books you can stack. And once you hit the ceiling, maybe, that's it. You can't stack any more books. So if your stack is full and you try to do a push, that's another error condition. And that's the famous stack overflow. So those are the two errors that can happen. And by the way, if we
I feel like we touched on this in another class. I don't remember.
we probably have.
270?
Yeah, 270 we talk about stacks.
Engineering?
Yeah, engineering 270.
Oh yeah.
Yeah.
Assembly language and microcontrollers.
Yep.
Yeah.
And so Stack Overflow, right, their little icon here is like a little tray that you can put things into, but there's too many things to fit in the tray, and so they're like spilling over. That's a pictorial, you know, representation of a Stack Overflow. So there's too much stuff in there. All right, so pushing and popping, add things to the stack, remove things from the stack. Possible error conditions, popping from an empty stack, pushing to a full stack. So why do we care about stacks? And one of the applications, probably the main application that we encounter for stacks in computer science is related to function calls. And so imagine this, we have a main program and we're doing some stuff, and at some point we say, you know, I equals function j. And we do some other stuff, and somewhere else we make, you know, k equals function of j. And we do some other stuff, and so on. And somewhere over here is our function fun. And it does some stuff, and it says return. So the way this works in the CPU, right, our main program starts, we do stuff, we come to this function call. We're going to somehow, you know, make j available to the function. Our CPU is going to jump over to this code here where the functions code is, execute all that code. When it gets to a return, it's going to come back here and continue. But the next time it does a function call from down here, it's going to go to the same place it did before, execute all that code, but this time the return is going to come back here. So this return statement is tricky. Sometimes it'll return here, sometimes it'll return there. How does it know where to return? Because when you make a call to the function, you figure out where you want that function to return to, and you save that somewhere. Now, you could just save that in a magic variable called, you know, return location. And so I could, you know, save this location in this variable return location, and this could say go to whatever is stored in return location, boom. And down here I could save this address in return location, and then the return would say go to the return location, boom, it'll come back here. But the possibility is that, you know, inside our function, we might call another function, function 2. And so when this function 2 call is made, this return address needs to be saved somewhere. Well, if I save this in my magic global variable called, you know, return location, this return will come back here. But when I come to this return, it's going to go back here also. In other words, if I've got this return address saved somewhere, and I've got a new return address that needs to be remembered, it needs to be stored somewhere else. I can't store it the same place I did this. So I need something like an array, or a linked list, or something that can store all of these different return addresses. So if this is address A1, and this is address A2, so I call function 2 and I get to return, where do I want to go back to? I want to go back to address A2. And when I come to this return statement, I want to go back to address A1. So when I make this function call, I want to save A1 somewhere, and I want to save it in such a way that that's the last return address that's used. This is a LIFO structure. This is a stack. So when you make a function call, what I actually do is I push A1 onto the stack. And if I draw a picture of a stack here, and imagine that we're adding things from bottom to top. When I push A1, A1 is sitting right there. When I get to my function and I start executing and I get to a call to function 2, that call statement will say, hey, when you're done, I want to come back to A2. It'll push an A2 on the stack. We come over to function 2. We come down here. We get to a return statement. It says pop the top of the stack and go there. So it's going to pop off an A2. It's going to come back here. Keep executing this. When I get to this return statement, it says pop the top of the stack. That's A1. It goes back to A1 and continues. Now we make this function call. It pushes the address of the next instruction A3 on the stack. We come over here. It makes a call to A2, so A2 goes on the stack. When we hit this return, A2's popped off. We come back here. Now when we get to this return statement, it pops off the A3 and it goes back here. So at the very least, stacks are used to save return addresses for function calls. And on the PIC processor, if you've done Engineering 270, that's all that's saved on the stack. When you make a function call, the address of the next instruction in memory is pushed onto the stack. And when you do a return, the stack is popped, and the value that got popped off, that's where the program counter is set to, so that it goes back to that location in your program.
So, in terms of what's actually getting stored on the stack, if you say had a void function, for example, it's not returning a variable, it's only going back to a location. It would only be storing the location, but in the event of something like an int-return function, it would be storing an address and an int variable.
So it really depends on the language and the compiler and the operating system and the processor to some degree. At the very least, you're going to store the return address, the address in program memory of the next instruction, so that you can return there. But in practice, you store a lot more than that on the stack. So you may store the values of certain variables that you want to preserve, so that before you return, you can retrieve those from the stack. But when you start a function, you usually store local variables on the stack. And so we do some funny business with the stack. We artificially throw some placeholders on the stack that we use for our local variables. And the way that function calls are made and returns are executed gets really complex sometimes. And so you can talk about the call frame, which is the totality of all the stuff that gets saved when a function is called and then gets restored before a return is made to the caller. And it's very dependent on the specifics of the operating system and so on. So on the VAX 780 processor, which ran an operating system called VMS, there was a very elaborate call frame structure that went along with saving values of registers and so on and so forth. There was actually a machine language instruction that would do all of this stack manipulation to save your call frame on the stack. And it was done in machine language. It was a single opcode that would do all of that. In C, this stuff is usually done through a bunch of assembly language instructions. And you can go in the debugger and make a call to a function, and in the debugger, look at what the stack pointer is before and after the call. And then after the call, you can look at the area of memory where the stack is stored, and you can actually start to untangle some of what's being done when you call a function, where the local variables are being set up, and so on and so forth. If you do a computer security course at a university, you get to dig into all of this stuff, usually with GDB, and actually take apart the call frames and see how all this works. And it's a really fun, if you like really low-level, detail-oriented puzzles, it's a super fun thing to do.
Might be jumping ahead way too much here too often, but it's just because I'm curious.
Okay.
Static tends to be a keyword that's a little bit different language to language.
Mm-hmm.
And I noticed in C, if you name a local variable prefixed with static, if you call that variable again, or that function again, the variable is going to have the same value.
Mm-hmm.
How would that relate to the stack in some way or another?
So the way I learned statics, and I've had a feeling for years that it's not valid anymore, but the way I learned statics was basically they're not locals that are stored on the stack. They're stored in a fixed location in memory, and you can always rely on that variable having the same value as long as your program is executing and nothing has changed it. Whereas most locals, if I have a function with a local variable I, and I call my function and I set I equal to 10, and then I exit my function, and then I call my function again, I might still be equal to 10, or it might not. It might change. And it's fairly randomish whether it changes or not. It depends what else is happening on the system. Whereas a static, you could declare, and it does not store it on the stack. It stores it in one location. But like I say, I've gotten the feeling, and I don't know where I got this, but many years ago I got the feeling that like that doesn't really apply anymore. But I suspect you could probably find a lot of information and misinformation on it online. And then statics in Java are just another thing.
And in C#.
Yeah.
I always found it kind of weird, like where would you want to use that and why would it be applicable?
Well, so statics are nice when you want to. It's kind of like a global, but without necessarily being global to like everything in your whole program. So you can make a sort of local global. And sometimes globals are important, right? You need to preserve something between function calls. Like every time you call this function, you want to read another line, another character of input from a file. Well, you might want to know, how many lines you've read, and you might keep that in a static. All right, and someone else says they've had a similar explanation for this, so we got 2 votes for statics. All right, let's take a short break. We'll come back. I want to talk more about why we care about stacks. This is sort of the quintessential computer science application of stacks, or the first application. But I want to talk about stacks in terms of other uses for them, and then I want to talk about how we implement them. And then we'll switch gears and start talking about queues. So let's do a break. And we are at 14:10, so we'll go 5 minutes. All right, so I'll be back in 5 minutes. Alright, so let's talk a little more about stacks. And stacks are actually fairly familiar to most of us, kind of from daily life. A lot of what we do in our day ends up using kind of an internal stack. For example, suppose you're going to take your dog for a walk. All right, so your goal is take dog for a walk. And so you decide you're going to do that, but it's cold outside, so you need to first put on a jacket. And so you have to find your jacket. And so you start walking around your house looking for your jacket, right? Now my goal is to take the dog for a walk, but before I can do that I got to put on a jacket. Before I can put on the jacket I've got to find the jacket. So I'm walking around the house by myself. My dog's looking at me like, hey, am I going to get in on this or not? Right? This is my current task. But I have some other tasks waiting in the background. Once I find my jacket, I'm going to put it on. And then I got to take the dog for a walk. I need to remember both of these things. Even though this is the thing that I'm doing, I need to hold these somewhere. Now, as soon as I find my jacket, I don't want to just go ahead and walk out the door with the dog. I want to put the jacket on, right? So I need to remember that this is a thing that I'm going to do. And so after I find my jacket, I remove that, and I put my jacket on so I can remove that. Now I got my jacket on, I'm ready to take the dog for a walk. Well, I need to find the dog's leash. So now I have to find a leash. And I started looking around for it, and I eventually find it, and I realize the dog has chewed it in half. Right? So I found the leash, but I'm not ready to take the dog for a walk. I need to get a new leash. And so how do I do that? Well, maybe I hop onto Amazon. And I find a leash I want to order. And so I put in my order, but I have to pay for it. So I have to, get my credit card, because I don't order from Amazon enough to memorize my credit card number. Certainly not me. So I have to get my credit card, right? And while I'm doing this, maybe my internet goes down. So now I have to, fix my internet. And my router's blinking funny. I don't know what it means, so I have to find the router manual. And the first thing that I put on my stack of what I was going to do was take the dog for a walk. And that thing is still sitting there at the bottom of my stack. And I'm doing all these other tasks. And when I finish these, I'm going to pop off the stack and eventually get back to take the dog for a walk. But it's this last in, first out behavior that governs a lot of what we do. And probably the majority, probably 90% of people tend to work with this last in, first out structure. And sometimes, it's necessary. I cannot, take the dog out unless I put a jacket on because I don't want to freeze, right? But sometimes, it's voluntary. We just think of something new, and so we go off and we do that other thing. It's like, I'm going to call so-and-so. Oh, but first, I want to do this other thing. And you're partway through that, and it's like, oh yeah, I should set my, something up. Go do some laundry or something. So this is sort of how a lot of us work. And life would be really, really different if you didn't do things like this. If I decide I'm going to take the dog for a walk, and it's like, okay, I'm going to do that first, and then I'm going to put a jacket on, and then I'm going to find my jacket, right? It just doesn't make sense. So this pops up in kind of day-to-day life. It also pops up when you're surfing the web, right? Which I don't think is a thing anymore. We don't surf the web. We do online research. But, when you're online and you're looking up information on, what is a Sentinel node, and so you Google that, and you're reading through the topics, and there's, a topic about something else that you're interested in, and so you click on that, and you start reading a story about, some new video game that's coming out, and it mentions, you know, this VR headset that it works with, and you click on that and you start reading about this VR headset, right? And you have a stack of pages that you were looking at. And when you click on a link to go to a new page, you're basically taking the place you are right now and pushing that onto a stack. And when you hit the back button, that takes you to the last thing that was saved on the stack, the page that you were on before you clicked to the current page. And once you get back to that previous page, guess what? All your previous pages before that are still saved. They're saved in a stack. And when you hit that back arrow button again, it pulls off whatever's now at the top of the stack, and it says, oh yeah, here's your current page. This is where you were. And if you hit the back button enough times, you end up back where you started, which was, you know, a blank browser window. So the implementation of that ability to, you know, click on a link and go to a new page, but get back to where you were, that's implemented using a stack. And there's a lot of places in computer science where stacks get used. All right, so some terminology and more concepts. So stack pointer and top of stack. If we envision a stack as you know, a pile of things. So I put A on the stack, and I put B on the stack, and I put C on the stack, right? You and I, if we just stack things up on a desk, we can see where the top of that stack is. It's the thing we see if we get above it and we look down, right? Computer can't do that. Computer is just memory and binary values. So we have something called a stack pointer, and it's usually just abbreviated SP. And the stack pointer helps you find where the thing on the top of the stack is. And there's a slightly more nebulous notion called top of stack. And top of stack, you know, is where the last thing on the stack is, basically. And it's kind of like the stack pointer, but stack pointer is what we actually use when we want to find what the current thing is on the top of the stack. So if this is what our stack looks like, and we say push a D will go there, and the stack pointer will change, you know, maybe to point to the D, and the top of the stack is now right here. And if I say pop, well, the stack pointer will look at the stack implementation, will look at the stack pointer and say, okay, this was the last thing that was put on the stack. Person who wants to pop, I'm going to give them a D, and I'm going to change the stack pointer to be right here. And so now this is where the top of the stack is. So the stack pointer can be wired up a number of different ways. It can point to, you know, the last thing that was added to the stack. It can point to where the next thing's going to get added to the stack. And we'll look at ways of implementing this with an array, and we'll see different options for the stack pointer. But either way, right, or whatever way you decide to interpret the stack pointer, right, you need some way, as you have a bunch of things on your stack, to know what's the last thing that was put on the stack. Because when you say pop, that's the thing you want to pop off. Well, a really useful way to implement this is using a linked list. And we've already done half of this in some sample code. Suppose we have, you know, our Sentinel node, and we want to push, let's say, the letter A onto our stack. I can just have the Sentinel node point to an A. If I want to push a B, what I'm going to do in my linked list is insert that B at the beginning of the list. So now my Sentinel is going to point to B, and B is going to point to A. And if I push a C, I'm going to insert that C at the beginning of the list. So my Sentinel will point to C, and C will point to what was at the beginning of the list, which is B, and B will still point to A. And let me push one more on there. Let me push a D. So sentinel points to D, to C, to B, to A. All right, now when I want to do a pop, all I do is remove the first thing in the list, and I give that back to whoever asked for it. So the first thing in the list, the thing the sentinel points to, is D. So I'm going to return to D, and I'm going to delete that from the list. Well, how do I delete the first node in the list? I just change the sentinel to point to whatever that first node is pointing to. So now my list looks like this. It looks exactly what it looked like after I pushed my C on before I pushed my D. So the pop undid the push. And now if I say pop again, the code will look at the thing that's in the beginning of the list. That's a C. It'll return that to me. And it will delete that from the list. So now my list looks like sentinel points to B, points to A. And now if I push a Z, it's exactly the same algorithm. I just add this to the beginning of my list. So my sentinel points to Z, points to B, points to A.
So, is this more of the reality of stacks, and it's less of just this chunk of memory that every time we hit a return, we're going to look at it and then pop something and then go to the next thing? It's more of like a linked list kind of structure?
So with this setup that I'm describing, yeah, this is a linked list structure. And this is you know, this slightly simpler version of the add function that I suggested to warm up with. And you may have noticed when we tested that and we pushed to 10, 20, 30, and then we printed our stack, it came out in the reverse order, 30, 20, 10. And so we add a pop function that basically just deletes the first node and gives us back that value. So let's look at this in code. Let's say we want to push a number n. Right, allocate some memory for a new node. Save your number in the data field. If we say new arrow next equals sent arrow next, new is now pointing to whatever the sentinel is pointing to. So I push something in here, I make my new node Z point to the same thing the sentinel's pointing to. It's pointing to B. And now change the sentinel to point to your new node. So sentinel points to the new node points to what was at the head of the list, and nothing else has changed. Everything else in the list is identical. So that's inserting in the beginning. And when I want to pop, I can do, you know, temp equals sentinel narrow next. Return value equals temp arrow data. So that's the data value of that first node in the list. And then I can say sent arrow next equals whatever temp was pointing to. I can free my temporary node from memory, and I can return my ret value. So there's a pop routine. So if my list looks like this, and I say pop, well, temp is going to be the thing the sentinel points to. Ret value will be whatever its data value is, so ret val equals, I don't know, you know, the character Z here with a number or whatever we got stored there. And then change sentinel next to B temp next. Well, temp next is B, so I'm going to change my sentinel to point to B. But I can still get to this node because I saved a, a variable temp that had its address. Now I'm going to say free temp. This is gone. I cannot access this or any of its fields anymore. But the data value I already saved in just, a local variable called return value. And so I can go ahead and return that. And so I've deleted the node from the list, and I can return its value. So where can this pop function blow up? Where's the segfault potential? Can it segfault? So segfaults usually come from trying to access a bad location in memory, typically null. And we know that the sentinel always exists. That's what the sentinel's for. And so sentinel arrow next will always exist. It will be the address of the next node. But if there are no more nodes, temp could end up being null. And when we try to do temp arrow data, that can potentially segfault. So in here we need to do a check. See if temp is equal to null. If it is, what does that mean? It's a stack underflow. Right? We have nothing in the stack, but we're trying to pop something. That's an error condition. So if you want to do something other than just blow up when you do a stack underflow, you need to put a check in here and do something accordingly. Now what you do depends on your implementation. But you could print an error message, you could throw an exception, you could return a special value. It depends on what you choose to do. But if you're trying to notice where stack underflow will happen, it will happen right here. Where's the error condition possible over here in the push? The only thing in here that could end up being null is the return value from malloc. We know that sentinel's not null, so sentinel next always exists. Once we get past here, if new is not null, new data exists, new next gets assigned a value, sentinel next gets assigned new. But if malloc returns a null, then this code's going to segfault. And the only time malloc returns a null is if you're out of memory. And if you're out of memory, that means you have a stack overflow. You have stuff on your stack and you're trying to push something else and there's no memory available for it. So without extra code, a stack overflow, stack underflow is going to cause a segfault. But we can detect those conditions specifically by looking for the exact situation that would lead to a segfault, which is this variable new being null or this variable temp being null. All right, questions so far?
So, if you tried to do a function call, and it would be the function call to do that would stack overflow, is there any way to tell prior in code that would happen and avoid it?
With this kind of stack with a linked list, it's a little hard to do because running out of system memory is such an unusual situation, and we could actually check before we do the push to see if there's memory available, and it might say yes, but between the time we do that and we actually try to do this malloc, something might use up that memory. So it's pretty hard to predict. But what's a better gamble is to find a way to manage this. For example, we could have our push function return an integer, which tells us whether we succeeded or failed to push. And if new is null, we'll just return a 0. Otherwise, we'll return a 1. And then whoever's calling the push function could check to see the return value and know if that push succeeded or if something's going on. And if it gets back a 0, it could print a message like, you know, sorry, we can't continue running your program right now. We're running out of memory. See you next week. Stack underflows are usually something you can prevent. In most cases, the program that's pushing onto a stack is the same one that's popping from the stack. And so if you're a little careful with your accounting, you usually won't stumble into a stack underflow. At least I haven't in situations I've used stacks. Because you know what you're pushing and you know what you're popping. But the overflow is often, there's only so much memory, there's only so much space in a stack. Sometimes you just need more space than is available, and you're going to overflow. So this is one way to implement a stack is with a linked list. Another way to implement a stack is with an array. And this is closer to what happens with a hardware stack. So most computers, most CPUs have one or more stacks that are implemented in hardware. They're actually a part of the computer architecture. Even the PIC processor we use for Engineering 270 has a hardware stack. It's a little section of memory. There's a bunch of flip-flops that store 1s and 0s, and every time you make a function call, the address of the next instruction gets saved by setting those flip-flops to the appropriate values, and a stack pointer records that you've saved a value on the stack and things are adjusted and so on. They're either flip-flops or really tiny capacitors. I'm not sure what their architecture is, but it's a digital memory. So yeah, 31 usable sets of 3 bytes for the PIC-18 F1220. Good memory. And so this is closer to how we could implement this with an array. So let's make a stack of integers, just for simplicity, and let me call my stack stack. I think if it was a Sesame Street Muppet, it would be called stack. So stack is my stack, and I'm declaring it to be big enough to hold 10 integers. So this will overflow if I try to push more than 10 things onto it. And I'm going to have a stack pointer. And let me draw a picture of my array. So there's my stack. It holds 10 integers. And stack pointer I'm going to interpret as follows. SP is going to be the index for the next push. And remember, stack pointer somehow tells me where the top of my stack is. So my stack is going to grow in this direction. The more I push, the more elements of this array I'm going to use. And so the top of the stack is going to move downwards on this piece of paper. It's going to move to higher indices and higher locations in memory. Locations with larger memory addresses. And you always got to be a little careful with the pictures of stacks you draw. Sometimes they're drawn like this. And sometimes they're drawn, from bottom to top. With the first things you push being on the bottom and more things being added above them. And it's just, convention of whoever's drawing the picture, but you always want to be clear which way is the stack growing. And this can cause a lot of lost time if you get confused about this.
It seems like you could also have an array sorted stack at a more software level rather than just a hardware level too, right?
Yeah, and this is a software stack that we're speccing out here. This is like something we could write in C. but it's going to mimic what gets done in hardware also. Sorry, go ahead.
Out of curiosity, in software, what's more common? Or is it a structure we just haven't spoken about yet?
What's more common among what?
If I make a function call in C, is it going to go to a stack structure that's more like a linked list or more like an array?
It's going to be more like an array. So this is going to be pretty close to what would happen with a physical hardware stack. Because main memory is basically like a big array. If you have 4 gig of main memory, it's basically like a 4 billion element array. And that's very much how you know, like the PIC processor stack basically looks at an array of 31 words, 20 bits each. So SP's, I'm just going to sort of decide SP, the value of that variable is the index where I'm going to do the next push. So I'm initializing it to 0, which means this first location in the array is where I'm going to push my first number that I push onto the stack. And if I say push a 10, I want to store a 10 right here, and I want to change my stack pointer from 0 to 1. Because the next push I want to have happen right here at location 1. And if I say push a 35, well, stack pointer is 1, I'm going to store my 35 at index 1, but I'm also going to increment the stack pointer so that the next time I push, I'm not going to overwrite the 35, I'm going to store it at the next spot in my array, which is 2. So I'll push a negative 17, stack pointer says store that at index 2. So I'll store my negative 17 and increment my stack pointer to 3. Alright, well if SP is where the next push is going to happen, then SP minus 1 equals the index for the next pop. In other words, right now my stack pointer is 3, while the last thing I pushed was at location 2. And so when I say pop, I'm going to decrement my stack pointer and return the value that was at that index. I'm going to return a minus 17. And when I say pop again, I'm going to decrement the stack pointer to 1. I'm going to find what's at index 1, which is a 35, and I'm going to return a 35. Now what about this might jump out at you from a security point of view?
If you had some important methods to keep your program secure, I don't know, maybe like cleansing input,
Mm-hmm.
and it was a function call, and you could potentially pop that, just straight pop that
Mm-hmm.
stack, and then continue as if that didn't happen.
Mm-hmm. Okay, that's one possibility. There's another thing going on here.
Could you put in numbers that give an index for push outside of bounds?
You can overflow your stack, so if you push too much, you'll overflow your stack, and that's another potential. And there's exploit opportunities there. The thing I'm thinking of, those are both valid concerns. The thing I'm thinking about is that, you know, I popped off a 17 and I popped off a 35. I removed them from my stack, but they're still sitting in memory. I actually haven't removed them from memory. I've just said I'm not interested in those anymore. I changed my stack pointer to 1, which means when I want to push something, I'm going to overwrite that spot right there. I'm saying these are unused, but the values that were pushed onto the stack are still sitting in memory. And so if I have something like a password or a credit card number or some kind of credential, and I push that onto my stack in some way, and then later I pop it off, I need to remember that pattern of bits is probably still sitting in memory. Unless you do something like change or pop to not just move the stack pointer, but actually overwrite what was stored there, replace it with zeros or an alternating pattern of ones and zeros or somethings, things that were on the stack will still be in memory and are potentially still accessible. If my program exits and another process starts running and it starts using the same area of memory for its stack, I might be able to pick up values from another program. And that's a big exploit opportunity. So it's just something to be aware of.
I've heard in general a lot of people these days are trying to avoid any kind of stack manipulation for those reasons.
Interesting. Yeah,
I don't know specifics, but go ahead.
It's interesting and it's a little scary. Every now and then people discover exploits that are pretty low level, that get down to, you know, something very, very basic, like the way function calls are made. And sometimes these issues have been lurking in the hardware for, you know, a decade, and nobody has found them. And you've got so much stuff built around this, it can be staggering to think about how are we going to mitigate this threat. And I think that's what keeps some security experts awake at night. And you know, this used to not be a concern because your computer was kept, you know, in a separate room, and you couldn't even like get access to it unless you had access to a physical terminal, and those were kept behind locked doors and so on. But you know, with everything open right now, you know, I can talk to a router at, you know, some other facility, and maybe they've got firewall software running and it won't let me get my packets through the router to the machines on the other side of their firewall, but I can still talk to their router. And if there's a problem with the security of their router, right, potentially that can be exploited. And, you know, unless you physically disconnect your machine from the internet, there's vulnerabilities out there. And that's fairly uncomfortable, I think.
I personally get a little intrigued when those really low level exploits can get found, and it's not quite as dangerous because you don't have immediate access to somebody's computer.
Mm-hmm.
They're pretty interesting when somebody does figure it out.
Well, and any one of those in the right hands becomes, you know, just this incredibly powerful tool to you know, pry the top off other people's machines. It does not take much. There's so much security in you know, modern operating systems and networking infrastructure and so on that really just a tiny little opening somewhere is enough to really just kind of like open things up wide. And you know, we get scared when we're told that someone has stolen our password, you know, because now they can like theoretically log into our machines if we have an SSH daemon running, you know. But it's those low-level exploits that I think are the scariest, because you know, computers don't know what they're doing in some way. They're just following instructions, and if you can change the instructions that are executed when a machine boots up, right, you can have this machine do something very, very different, like, you know, log keystrokes and send them out periodically every time you go to a certain website or whatever. So yeah, it's a little scary, but it's also fascinating. So yeah, if you get to take a cybersecurity course, I definitely recommend it. I think it's one of the coolest ways to dig into the workings of computers is through this perspective of security. And I had a student who took this sequence a number of years ago, and he started getting into ethical hacking. And he got some good books with some exercises on it. And he would come in and he would show me what he was working on, and it was great. It was like the best exercises you could imagine for you know, working with the debugger or understanding pointers or things like that. It's a really rich way to dig into a lot of this stuff. All right, so let's look at pushing and popping with this array-based implementation, and all we really need to know is what the stack pointer is doing. If the stack pointer is the index for the next push, then our push function can look like this. Stack bracket SP equals n. That will take the thing we're pushing and it will save it in our array at the index given by this variable SP. And after we do the push, we need to increment our stack pointer to point to the next location in the stack. And we can actually do this post increment. We could do stack bracket SP++. And SP++ says, you know, first use the current value of the stack pointer, and then set stack pointer equals stack pointer plus 1. And our pop just returns stack bracket, and we'll do a pre-decrement. We'll say subtract 1 from the stack pointer and then use that as an index into this array and return that value. And so if stack is equal to 1, this call to pop would say decrement the stack pointer, change it to a 0, and now return stack element 0. That would return our 10, which returns the first thing that we pushed. So push and pop, right, are theoretically one line of C code, except for this business of exceptions, right? We need to know that the stack pointer is not 0, because if SP is equal to 0, which means an empty stack, then we're going to decrement it -1. We're going to try to return stack bracket -1. Well, that's whatever happens to be stored in memory before our array. And, you know, best case, it's some random value. Worst case, it's a segmentation fault. And in this case, if the stack pointer is equal to 10, this is going to give us an error because our array is only set up to hold from index 0 through index 9. And if our stack pointer is equal to 10, this is going to try to store n in stack pointer bracket in stack bracket 10, which is going to write into this location, which again at best is, you know, some other variable. At worst is a segfault. Actually, it's probably worse if it's some other variable because it corrupts your memory without telling you. So segfault's probably a better response here. So you need to do something in here to make sure you don't overflow, you don't underflow. But logically, right, it's basically just use this to access your array and then adjust your stack pointer. And it's worth mentioning that there's actually at least 4 versions of push and pop. This version is based on the idea that SP is the index where the next push will occur. But you could instead say SP is the index where the next pop will occur. And so if we do that, so here's version 2. SP is the location of the next pop. So now my pop instruction would use SP to find the thing that should be popped, and then after you pop it, you're going to decrement SP. So my stack is still growing in this direction. Top of the stack is towards the bottom of the page, higher indices. But when I pop, I use the current value of SP, and then I decrement it. And so push would want to take stack, and it would want to increment the stack pointer first and set it equal to n. And I would want to initialize my stack pointer to -1. So if I want to push a 10, I would increment the stack pointer to a 0, and I'd save at location 0. And if I want to push a 20, I would increment the stack pointer to a 1, and I would save at index 1. And if I say pop, I would use the current value of the stack pointer, which is 1. I'd see what's at location 1, and I'd say, okay, I'm going to return a 20, and I would decrement the stack pointer to a 0. And in this case, my empty stack is represented by my stack pointer equals -1. And my stack would be full when my stack pointer was equal to 9. And if my stack pointer was 9 and I tried to push, I would increment it to a 10. That would give me an error. So push and pop look exactly the same in both of these cases, except that in version 1, push was a post increment. In version 2, push is a pre-increment. In version 1, pop was a pre-decrement. In version 2, it's a post-decrement. And we can have versions 3 and 4 which look just like this, except we grow our stack from larger indices to smaller indices. And so push would involve decrementing the stack pointer, and pop would involve incrementing. And there's no right or wrong. It's 4 different flavors. A lot of hardware will do this. It will grow the stack in the direction of smaller indices. And this is why when we go into GDB and we look at local variables and they have addresses like 7FFF, and each time we get more and more variables, these addresses get slightly smaller. Well, this is, a location at the halfway point of memory, and our stack is growing in this direction. And the more function calls you make and the more variables you save on the stack, the smaller the address of those variables. And so on the PIC processor, things grow in this direction. The stack moves down. You start at element 0. You increment the stack pointer before you push, and element 0 doesn't actually exist for some reason. On an ARM processor, you can actually specify which of these 4 versions you want. There's configuration bits you can set up in a status register to say, do I want to do post-inc, pre-inc, post-dec, pre-dec. So it's flexible.
There's also like the flexibility of endianness in ARM.
Oh yeah. Yeah, and I think we'll get into endianness when we dig into GDB in a few weeks. But yeah, that's a whole nother issue, and I think that's settable in ARM. I think you're right. All right, and yeah, someone said in chat, instead of a stack pointer being an index, you could actually use the address. That would work just as well.
So it's more an issue between the flavors of like inclusivity versus exclusivity with pre-inc and post-dec, and
it's really about how you interpret, in this case, like what the meaning of SP is. You don't really gain or lose anything in one approach versus the other. But for example, if I grow my stack in this direction, I can start with a very, very large memory address and be pretty sure that as I move up, right, I'm going to hit memory addresses that don't exist before I get to location 0. And so I'll probably put my code at low memory addresses, and as your code gets longer, grow to larger ones. I'll put my stack at a high address and grow towards lower, but there's going to be, a dead person zone in the middle where there's just no physical memory. And so that's going to prevent my stack from accidentally bumping into my code, because if my stack decreases too much, I'm going to hit this area that doesn't exist before it gets so small that it starts interfering with my code. And if my code grows, it's going to hit this area of memory that doesn't exist before my code ends up getting stored in my stack. And so this was a way that earlier operating systems sort of mapped out how they were going to use the memory of the system. And so having stack growth in that direction can be useful.
Well, if you assign your stack to the heap to begin with, that wouldn't be a concern, right?
Well, it's hard to put a stack in the heap, I think, because the heap isn't sequential. And this sequential nature of stacks is really useful for some other things. So what we haven't really talked about, and this can take us astray if we're not careful, but when we make a function call, not only do we save the return address on the stack, but we do this thing where we artificially bump up the stack pointer. So let's say this is what my stack looks like, and I put some sort of return address here, and my stack pointer is pointing right here. I might actually reserve a bunch of locations in here and move my stack pointer down here. And I'm not doing this to push and pop. What I'm doing is I'm trying to get a block of memory that I know is mine. Nothing else is going to step on it. Because, you know, as long as the stack pointer is here, nothing above that's going to get touched. But I can store my local variables in here. And when my function exits...
Right? Because everything's stored sequentially instead of just fragmented on the heap.
Say the start of that again?
We're doing this because of the sequential structure. It's just so much quicker than a fragmented heap, right?
Mm-hmm. Yeah, yeah.
Okay.
But the other advantage is that, you know, when we return from our function, we can take the stack pointer and change it back to here, and bingo, all that memory we were using for our local variables is released. It's available for other processes to use. Because that's the nature of the stack, right? Once we put the stack pointer here, all the stuff at higher addresses is free. And if something needs to save something on the stack, it'll reuse this location right here. So it's a really, really fast way to allocate a bunch of memory and then have it automatically be freed when you return. And so if you dig into, you know, what function calls look like and how the stack is adjusted and so on, you'll see this happen. And if you take a local variable and set its value, you can go up in the stack and you can actually see where that value is stored. And that's pretty fun. And I strongly encourage, you know, if you have time and inclination and can spare, you know, the cycles, play around with this stuff. You know, we've got open access, we've got source code for all the tools and operating system and everything, right? Just make a main program, call a function, pass some variables, set up some local variables, and then hop into GDB and, you know, set a local variable equal to, you know, hex dead beef, and look around in GDB, see if you can find where that variable is stored. See if you can find what happens to it when you return from that function. See if you can recapture it after you've exited that function. This is all, you know, fun stuff. I mean, you can do programming as lab work, and I think that's you know, at least as much fun as, you know, listening to a discussion on how this stuff works or watching a video on it. Getting in there and getting your hands dirty is always good fun. All right. So let me talk briefly about stacks as an abstract data type. And I'm going to try to wrap up here in the next few minutes because I've been running over. But let's think about stacks as an abstract data type. Remember, an abstract data type is looking at how a user interacts with something, right? And from the perspective of a main program, what do you want to do with a stack? Maybe you want to do some sort of initialization. You definitely want to do a push. You want to do a pop. And maybe you want to know, you know, is my stack empty? And maybe it's possible to know, is my stack full? And maybe you want a reset option, which says just forget everything I pushed on the stack. And, you know, there could be other things, but this might be your view of a stack. And it's your view of an abstract stack. Whether you're implementing with a linked list or with an array, and if you're using an array, is your stack pointer incrementing or decrementing? Regardless of those details, right, this is how I see the stack. I can initialize it, I can add something, remove something, I can see if it's empty or full, I can throw away everything on the stack. But what do these functions do? Well, if I have a linked list version of a stack, and I want to pop something off, I need to go to the Sentinel node. I need to look at the thing it's pointing to. I need to save its data value. I need to save its address. I need to change the Sentinel to point somewhere else, free that node, and then return the saved data value. If this is implemented using an array, I need to adjust the stack pointer and return an element from the array. Two very different sets of code, right? But to the caller, all I'm going to say is pop. You know, pop off the top and give me back the value you popped. And so this is how we interface with a stack as kind of an abstract data structure, an abstract data type, ADT. And again, you know, you could implement a stack by every time you say push, it sends a text message to someone and says, hey, push the number 12, and they write a 12 on a piece of paper. And when you say pop, it sends a text message and says, tell me what the last number is on your piece of paper, and they text you back a 12, and the pop function returns a 12. And however this is implemented doesn't matter to the main program, because the main program just talks to the stack implementation through this fixed interface. Alright, so this is this firewall that we're trying to set up in PA1, where you can add, you can search, you can delete, and so on and so forth, without worrying about, you know, sentinel nodes and mallocs and nulls and all this kind of stuff. Well, same thing with a stack, same thing with every data structure we talk about. We want to think about, just as an abstract concept, what is a stack? It's a thing you can push things onto, you can pop things out of. But as an implementation written in code, right, it might be this kind of stuff. Or it might be this kind of stuff. But those...
Have a reason, go ahead.
No, go ahead.
Would you ever have a reason to implement your own stack rather than just use the default one?
Yeah, definitely. So the default stack, the hardware stack, number one, you don't really have direct access to it through C or other languages. Number two, it's going to work in a very particular way. It's generally going to store addresses. And if you wanted to store, you know, characters on a stack or doubles or something like that, that might not work well. And so yeah, a lot of times in software we would use our own version of a stack. But, you know, when we get to Java, there's packages available for us, class libraries, that have implementations of all of these data structures, and we'll really just use those. And those are made for us and come with lots of nice little bells and whistles and features. But yeah, if you wanted to make like a calculator program, calculators are a good example of where we can use a stack. You would probably spin out your own stack package and use that.
It seems kind of like in some instances you would need to make your own thread pool, separate from maybe one that a language would have of things to do. Maybe you would also do a similar thing with a stack of tasks you need to get done that is separate from like the function call stack.
Yeah, that's probably fair. The hardware stack is great when you're in assembly language, because you're usually dealing with just sort of, you know, kind of like low-level binary objects. But I don't know. I never actually thought about like repurposing it for saving things in a software stack. Mostly, I think it's just that, you know, we don't really have access to that very easily from C. You can do inline assembly from C, for example, but we usually don't. And that's like a hardware detail. And, you know, it's possible other things are... We would need to know all the details about how that stack is being used and what's using it before we can start doing things like playing with the stack pointer. That would be faster than doing a software stack in C, but probably fairly risky. Meaning you just need to know a lot of details to do it without tripping up. But that's a cool concept. Alright, so we're going to call it good there. And remember, Monday is a holiday, Martin Luther King Day, so if you have classes on Monday normally, you don't have them this coming Monday. We will be back Tuesday, and we're going to talk about queues, which are similar to stacks, but they're a first-in, first-out structure instead of a LIFO, last-in, first-out. So we'll talk about queues, we'll implement them with linked lists, we'll implement them with arrays. and then we'll go on from there to some other structures. All right, so have a great weekend, and enjoy the long weekend if you get Monday off, and I will see you next time.
I have a quick question.
Yeah.
Code. So is there a way for PA1 to hard check if we're out of memory?
Every time you call malloc, check the return value from malloc. If it's null, you're out of memory.
Okay.
So when you're and don't worry about it inside a init, because a init has no way of dealing with that. But in your add function, check to see if malloc returns null. If it does, then return a 0 from add.
All right, thank you.
All right, you're welcome.